Thank you very much for the opportunity to present in honor of Chris. And Chris actually did all the oxygen analysis in this talk. So thanks, Chris. And I'm going to take you to Iceland now. See that little white peak in the rear? That's Eyjafjallajökull. You may remember 2010. But I'm going to talk about KATLA, which is the big volcano in the front. So KATLA is most well known, certainly in Northern Europe, for the Brothers Lionheart, the big dragon in there. That was actually KATLA. And more recently, we had the Netflix series where the unrest inside the volcano caused all these perished people to wake up again and created volcano zombies. And one day I'd love to talk to them, but well, I'm not sure how real that is. So we have to do some geochemistry to get better information, I fear. And let's start with two types of volcanoes in Iceland. There are central volcanoes and fissure eruptions. The current activity on the Reykjanes is a fissure system, but if these systems build up over longer time and have a polygenetic origin, they make stratovolcanoes and potentially large calderas, as we see at KATLA. So KATLA is a large volcanic system in the south of Iceland. It's almost 1,400 meters tall, 14 kilometers wide, and it sits under a large glacier. It's very active. 20 eruptions are documented between, well, in historical times, between the settlement and the last eruption was 1918. It erupted over 180 times during the Holocene, and the eruption volumes, they vary a little bit, and they can reach several cubic kilometers. The last eruption, as said, was 2018, but there was unrest in 1955, 1999, and again 2011. There could have been some subglacial volcanic activity that we haven't been able to observe. So the largest silicic eruption from KATLA is the Solheimar ignimbrite, erupted about 12,000 years ago, and it produced about 7 cubic kilometers of pyroclastic materials. There's a whole series of silicic tephras, the silk tephras as they're known. They have smaller volumes, but they seem to erupt quite frequently, certainly throughout the Holocene. And I should add, KATLA is believed to be one of the largest volcanic carbon dioxide emitters, and current estimates are at 4% of the global volcanic carbon. I personally think it's maybe a little high, but it certainly produces a lot of CO2. What I want to talk about is this ancient problem. It goes back to Bunsen, 1951, the chap that invented the Bunsen burner. He went to Iceland and realized there is a bit of an issue. And the origin of silicic magmas has puzzled us since then. There is two schools of thought. There is model one, fractional crystallization, closed system fractionation, and the alternative is partial melting. I'll try to convince you today that actually I think we don't need to be thinking so rigidly, because I have a proposal that we are somewhere in between in reality. So having this kind of ancient discussion coming back, I think is almost, well, a thing of the past. Let's see whether I can convince you with my data. So here's KATLA, and this is the samples. We analyzed samples from a previous study, Lacasse et al. 2007, and we did 57 U-hole rock analysis and 5 feldspar separates to test if the feldspar and the whole rocks are in equilibrium, and that makes a total of 62 new analyses that we're offering. So just a very quick point here about the rocks. In the top row, we have mafic rocks, basaltic rocks, then intermediate ones. We have very few intermediate ones. And then we have felsic rocks. There's a dirty looking pumice in the bottom left. And there we have a bunch of xenolith as well. And these are silicic xenolith with partial melting textures. So here's a few impressions from the SEM. And there we have all those things that are quite characteristic. We have crystal clots, we have nice plagioclase and pyroxene, and they look euhedral. And we also have these xenolith, as I mentioned, with partial melting texture. Here's a little one in our slide. And if you zoom in, you see these symplectites. So they clearly have experienced a remelting event. If we look at the major elements to get us going, here's the task diagram. We see that the basaltic ones in blue, they are, of course, in the mafic part of the diagram. Our intermediate ones, the green ones, are spread out. And as I said, there's very few of them. And the silicic ones, including the xenolith, they plot at the high silica end of things. Our data overlap with previous studies, so that's comforting. We believe them to be representative. There is some tephra analysis that seem to fill that bimodal gap. But I talked to several people, and it's hard with the tephra. It may well be mixed. So it's not entirely clear whether we have these intermediate compositions present in large quantities. Here's a few more plots, various major elements, Harker plots, and you see the basaltic and the silicic groups are always distinct. They don't really overlap, and the intermediates, they don't really connect them either. So we have a bimodal suite. And this bimodal suite is not untypical for Iceland in general. When we look at the traces, here we have a multi-element variation diagram. Again, the felsic ones are in orange and the mafic ones in blue. And in pink, we have our xenolith. The xenolith and the felsic ones are virtually identical. They overlap. It's, to me, the same kind of material, chemically speaking. And we see a big strontium anomaly, a negative one, and a europium anomaly. So I guess the takeaway point is that fractionation of plagioclase did play a role, very hard to explain otherwise. And that's a good takeaway point. But let's look at the oxygen now. So here's a bar chart. Let's start with that. The gray vertical bar is the mantle, and then our data are plotted in the colorful bars at the bottom. There's a few reference suites there. Fresh Icelandic basalt obviously overlaps with the mantle. And then we have Askja. Askja is known for low delta 18O signal, KATLA as well. And our basalts overlap with the mantle as well. There's small outliers on the far right, but they don't really go to very negative values. The intermediates are almost the same, but the silicic rocks, they push towards the left. The darker dots are actually the feldspar separates, and the lighter orange dots are the whole rocks. And our xenoliths, they really shoot off towards the far left. They have negative values. So the felsic xenoliths, they seem to be the most intensely hydrothermally affected materials, but we don't see much hydrothermal mineralogy in them, so I assume they have been cooked and have lost melt, and that means they could have been even more negative before that event. So I mentioned there are some outliers for the basalts, and I'm not sure, yes, it works. That's the LOI values, and these outliers are actually very hydrated, so we have to ignore them for the rest of our consideration. When we look at the delta 18O versus silica plot, then there's this slightly rising line there. That's the fractionation line, and Ilya pointed this out as well. So when we have variations on that, then we need to think a little bit, because then it means we have something going on beyond closed system fractionation. The basalt suite largely overlaps with the mantle array, so that's good news. We don't have any awkward negative oxygen isotopes coming from the mantle, but our felsic rocks, they shoot towards these crustal xenoliths, and therefore we see a variation that's going towards lower values. Only 2 of our samples actually fall on the fractionation line, meaning that, well, fractionation in a closed system is not the key process that is going on there. We tried to model this, and this was done with help of the magma chamber simulator package, which is an energy-constrained AFC model. And here, it looks a little complicated, but let me run you through this. What we do there is we take rocks, packages of rocks, and we put them in the magma reservoir, and we do this multiple times over the course of fractionation. This is why you get these step functions. We did this for 5% assimilation, 15 and 25. You see the little kind of color codes in the bottom. And let me bring you to a larger version of this. So there we actually seem able to reproduce most of our felsic data with something like 20 to 25% of assimilation for the most extreme values. And this holds true also for our trace elements. So here we see the same, and we're touching the lower end of the silicic ones with our 25% assimilation. So most would require a little less, but overall we are pretty happy with that result. And that would imply that we are actually thinking about AFC-style processes, fractionation coupled with assimilation, and therefore maybe it's no surprise people find evidence for fractionation, evidence for assimilation, but there is a way to put them all together. So that brings me to the wrap-up slides. This is a model by Jedi et al. This is the seismic tomography, and if we put our reservoirs into that system here, then we're dealing with a deeper reservoir that's basalt dominated, and the basalt range is about 5 to 6 or 5.1 to 6.1, therefore very mantle-like. But the felsic rocks are much lower in oxygen, apart from 2 individual samples, and that means we're assimilating something with a low delta 18O component and substantial amounts of it, potentially up to 20-ish%, and that has to happen in the upper part of the plumbing system because we need to have the meteoric water to actually do that. So this is the kind of summary, and in conclusion, over 95% of our analyzed silicic volcanics at KATLA, they show a low delta 18O signal. It's very clear, and assimilation of up to 25% is needed to explain the spectrum of samples, and our xenoliths are actually surprisingly well matched to explain this. So to use a term that I actually learned from Chris as a PhD student, this is a bit like self-cannibalization of the volcano, taking materials that are very similar, but they have been residing in the system, and therefore they have been modified in their oxygen signal. The basalt samples that we have analyzed, they're very narrow. There is no need for some deep, low delta 18O mantle component, and that's very comforting. And on balance, neither fractionation nor assimilation seems to fit perfectly, and maybe AFC is the way forward. So I suggest that people may want to try something like the magma chamber simulator to see whether it applies to some of the other Icelandic suites. In terms of the plumbing system, well, basaltic magma with a mantle-like delta 18O comes in. It differentiates at the base of the edifice, and we don't see any major variations there. If there's different mantle components, well, they don't seem to be distinct in oxygen. Very similar to the recent work we did at Fagradalsfjall, which is in Bindemann et al. 22. And in the second stage, higher up in the plumbing system, assimilation and fractional crystallization, and potentially also some mixing, can explain the uptake of a low delta 18O signal into the silicic magmas, and it's certainly not a closed system for all we can tell. And if you don't believe me, maybe you want to watch the Netflix documentary and see whether there's more information to discuss. Thank you. And if you want, the paper has just come out a few weeks ago. It's, of course, open access. If you're interested, all the details are in there. And I say thank you for your time, and I hope there's time for a question.